So at the top here we have rewritten Q, what we had at the bottom of the previous slide, and we want to know the sign of Q because that will tell us if we have a minimum or a maximum. Alright, so recall that this is going to be positive, okay, because it's squared. So we need to know the sign of this bracket here. Okay, is this positive or is this negative? All right, so we work it out as follows. First of all, if we take this determinant here, all right, we'll look at now where it comes from, but if we look at this determinant and we work it out, okay, this is what we get here, and you can see that it's the negative, all right, of what is in this bracket. Okay, so this determinant is called the bordered Hessian, and as you'll see now, it's simply derived from the first order conditions. Okay, and just remember that a Hessian, as we looked at in the previous topic, is a determinant with second order partial derivatives as its elements. Alright, so if we have a look at the utility example that we've been working with thus far, I've rewritten the Lagrangian function here, as well as the three simultaneous equations that make up the first order condition. Alright, the way that we would get the bordered Hessian is by working out the second order partial derivatives, okay, working with these three equations here. So let's start with the first one, all right, where we've got L subscript lambda, all right, and if we were to work out the derivative of this with respect to lambda, okay, if we look for the term with lambda, we can clearly see that there is none, so that would be 0, all right, and that's what we have here. The partial derivative with respect to x1 minus 4 we've got here, and the partial derivative with respect to x2 minus 2. Moving on now to Lx1, okay, partial derivative with respect to lambda minus 4. With respect to x1, there's no term with x1, so it would be 0. With respect to x2, we'd have a 1 here. There we go. And moving on to this equation here, partial derivative with respect to lambda minus 2. With respect to x2, 0. Be there. And with respect to x1, it would be 1. Okay, so this here is our bordered Hessian, all right, and it's derived from these first order conditions here, all right, and if we express this using the more general notation that we looked at a few slides ago, then we would have the notation as follows. All right, so we need to work with the bordered Hessian in order to work out the sign of this bracket here. So if we calculate the value of our bordered Hessian and we get a negative value, it follows therefore that with this being negative, then what we have in the brackets here must be the opposite sign and hence positive. Okay, and vice versa. If we take some simple numbers, all right, for alpha, beta, A, B, and H, all right, and first of all, substitute them in to the bordered Hessian, to this determinant here, all right. Working it through, you see we'll get a value of minus 60. If we then take what we have in the brackets here, all right, where everything is the same other than the signs, and plugging in the same numbers, you'll see we'll get the same number but with the opposite sign. All right, so we can now see how we can work out the sign of Q. Because remember from the previous slide, the bordered Hessian, all right, the way in which we calculated that was to take the first order condition, the equations from the first order condition, and work out the second order partial derivatives. Okay, and that is effectively how we got these values here. All right. So now if we calculate a negative value, for example, for the Hessian, the bordered Hessian, it follows therefore that this value here would be opposite, okay, the opposite sign, it would be positive, okay, and given that we know that this is positive, all right, if we have two positives, all right, then that means that Q is going to be positive. But remember now, Q is simply our second order differential. Okay, it's d2z, all right? And remember, it's the sign of the second order differential that will be able to tell us whether we are dealing with a positive, whether we are dealing with a minimum or a maximum. All right, so this is what we have at the bottom here. Right? If we have a bordered Hessian that is less than 0, that is negative. Okay? With our bordered Hessian being negative, the value of what we have here in the brackets will be positive. Okay? With this positive and this positive, Q, okay, going back down here, Q, which we know is d2z, will be positive. And when our second order differential is positive, we know we are dealing with a minimum. Okay, and obviously with the opposite signs, we have the opposite conclusion. So if the bordered Hessian is positive, all right, what we have in the brackets here is negative. A negative and a positive gives us a value of Q, which is negative. Okay, in other words, d2z is negative, and that indicates that we have a maximum. All right, so just going back to our utility maximization example, we've got here the bordered Hessian that we calculated on the previous slide, and if we work through that to work out the value, you see that we get a positive value for the bordered Hessian. Okay, and with that being positive, okay, with the bordered Hessian being positive, d2z will be negative, and that indicates that we do indeed have a maximum. All right, so the values that we calculated for x1 and x2 going a few slides back, do indeed indicate a maximum. Here we have an example for you to work through, and you are asked to find the extremum of this function here. You aren't told if it's a maximum or a minimum, okay? And you are subject to this constraint here. Okay, so it's constrained optimization. You're going to need to work through the first order and the second order conditions. All right, so you can see them down here, and your starting point needs to be to set up the Lagrangian function, okay, which we have here. All right, and then to work out the first order condition, which is this set of simultaneous equations down here, all right, where we just work out the partial derivatives of the Lagrangian function with respect to lambda, x1 and x2. Okay, so that's what's set out here, and they all need to be set equal to 0. All right, and as we did with the utility example, we then need to work with these functions here to work out the critical values of x1, x2, and lambda. All right, and as we did previously, and you need to work through this yourself, you'll be able to find the values for lambda, x1, and x2. All right, so we now have values for x1 and x2, but we still don't know if we are dealing with a minimum or a maximum. So now we need to move on to the second order condition, which we've just been through, and we need to work out the bordered Hessian, okay, as we saw on the previous slides. All right, and the thing to remember now is that these elements here are nothing other than the second order partial derivatives, okay, which we would work out from these two first order partial derivatives here. Okay, so that is where we would find these elements here, and these ones here on the border, all right, the gx1 and gx2, these are the first order partial derivatives of the constraint. Okay, that is in effect how you would get these, or where these values come from here. All right, but the bordered Hessian we can calculate by looking at these equations here in the first order condition and working out the second order partial derivatives. All right, so doing that, we would be able to work out the values that need to go into the bordered Hessian for this example. All right, and working out the value of the determinant. If you work through all of this, you'll be able to see that we get a negative value. All right, and as we saw on the previous slide, when we get a negative value for our bordered Hessian, that means that we have a minimum.